Okay, so in this problem we have a little mechanism here, and it has three different rotation rates embedded in it, and we're told that all of those rotation rates, omega 1, omega 2, and omega 3 are constant. We're additionally told that the capital XYZ axes are fixed, and that the little XYZ axes are attached to the disk. And at the instance shown, A is directly above the center B of the disk, and the little x and the YZ and capital XYZ axes are aligned. And in this problem, we're asked to determine the velocity of point A as well as the acceleration of point A. Now, I'm going to do something here that maybe at first seems inappropriate, but I think is going to make our life a lot easier, and I'm going to make one slight change here. I'm going to take these axes, which I originally told are attached to the disk, and I'm going to make a strategic change here, and actually attach these axes to be on and rotating with this arm OB instead. And this is a subtle difference. You can solve the problem either way, but I think you're going to like this approach a little bit better. Why do I do this? Well, it turns out that if I make this subtle change, namely by attaching the axes to the arm rather than to the disk, that it's much easier to describe the motion of what's going on at point A. Namely, what we have is a rotating axis set, which only has 2 rotations associated with it rather than 3. And I think you're going to like that a lot better. So with this in mind, what we can do is we can start out by saying that the omega now is going to be the omega of the rotating reference frame. And in this case, it's going to be omega 2 about the capital J axis, plus in this case, a minus omega 1 about what I've called now the little I axis. Now we can express that in a consistent vector set, but for now I'm going to go ahead and compute the angular acceleration of that rotating frame. So using the product rule of differentiation, this is going to give me omega 2 dot in the capital J, plus omega 2 in the capital J dot, minus omega 1 dot in the little I, minus omega 1 in the little I dot. Now we were already told in the introduction to the problem that the rotation rates are constant, which means the first and third terms here go away. And likewise we know that the capital J unit vector is one which is fixed in space, and so the second term will go away as well. So we're left with an alpha here, which is equal to minus omega 1 times I dot, which we know is omega cross the unit vector I. If I go ahead and substitute from up above, I'm going to have this is equal to omega 1 times quantity omega 2 in the capital J, minus omega 1 in the little I, cross with the little I. And at this juncture, and only this juncture, I'm going to note that at this instant in time, the unit vectors little I and j are aligned with unit vectors cap I and j. And so what I can do here is I can go ahead and substitute without major impunity. So if I do that coming back up to omega, I can say this is equal to omega 2 in the capital J minus omega 1 in the capital I. And here, for example, down below, I can replace these little i's with capital I's and use it to great effect. And if I do that, what I'll end up with here is that I have minus omega 1 times omega 2 times capital J crossed with capital I, which is going to give me omega 1 times omega 2 in the capital K, with of course the minuses canceling each other out. So now that I have those, I can go ahead and work on trying to find the velocity and acceleration of point A. So to start with the velocity of point A, I can say that the velocity of point A is going to equal the velocity of point B plus the velocity of A with respect to B as seen by our observer, who is now attached to and rotating with bar OB, plus the angular velocity of the rotating frame across the position vector of A with respect to B. If I go ahead and do a little work here, I can start by finding the velocity of point B. And so to do this, I'm going to note that the velocity of B is going to equal the velocity of point O plus the omega of BO crossed with R of B with respect to O. If I go ahead and expand this out, because O is on the center rotation of the whole mechanism and it'll have 0 velocity, I'm going to add to that omega of BO. Now, all we really need to worry about here is the rate omega 2 in the capital J, and that's because B lies on the center of the axis of rotation associated with omega 1. And I'll cross this with R of B with respect to O, which is a distance B in the little I direction. Again, I can note that in this instant in time, the little i's and capital I's are aligned, so I can make that substitution now. And if I do that, what I'll have here is the velocity of B is equal to minus omega 2 times B in the K direction. I can take this result now and substitute it back into the velocity of A. So what I'll have here is the velocity of A is equal to VB, which is minus omega 2 times b in the capital K, plus the velocity of A with respect to B relative to the observer, which in this case is going to be minus r times omega 3 in the little I direction, plus the omega of the rotating frame, which we said was omega 2 in the capital J, minus omega 1 in the little I, cross the position vector of A with respect to B, which is a distance r in the little j. If I again introduce the equivalency of vector sets here, I can expand this, so I'll have minus omega 2 times b in the capital K. Little I is the same as big I, so I'll have minus r omega 3 in the big I. J is going to be replaced by capital J, so J cross J is 0. I will be crossed with capital I, and J will be crossed with capital J, so we'll have minus omega 1 times r in the capital K. So if I go ahead and put these together, I'll have that velocity of point A is equal to minus r omega 3 in the capital I, plus minus omega 2b minus omega 1 times r, all in the capital K. Okay, so now that we have that, I can also work out the acceleration of point A. So if I do that, I'll have the acceleration of point A is going to equal the acceleration of point B, plus the acceleration of A with respect to B as seen by our observer, plus the angular acceleration of the rotating frame cross r of A with respect to B, plus the Coriolis term, which is 2 times omega cross the velocity of A with respect to B as seen by our observer, plus the triple product term, which is the angular velocity of the rotating frame crossed with the angular velocity cross r of A with respect to B. This will be one of our longer computations of the semester, so to help us out, I'm going to start by looking at the acceleration of point B. I can say this is equal to the acceleration of point O plus the angular acceleration of link BO cross the position vector B with respect to O, plus in this case omega BO cross quantity omega BO cross the position vector B with respect to O. If I expand this out, I know the acceleration of point O is 0. I know that alpha BO, because that rotation is a constant rate, will be 0. And the next term is going to give me omega BO, which I said was omega 2 in the capital J, crossed with quantity omega 2 in the capital J, crossed with B in the little I. If you go ahead and plug through the math here, you're going to find this is equal to minus omega 2 quantity squared times B in the capital I direction. I can take that result now and substitute it back into the acceleration of point A. So I'll have the acceleration of point A is equal to AB, which we just found was minus omega 2 squared times B in the capital I, plus the acceleration of A with respect to B relative to the observer. If we go back to the drawing, you'll note here that the observer is attached to BO, and so what are they going to see for an acceleration? Well, what they're going to see here is that point A is doing circular motion about them, and because the rotation rate omega 3 is a constant, I'm simply going to have a centripetal acceleration like term here. So I'm going to have minus omega 3 quantity squared times r in the little j. I'm going to add to that the alpha, the angular acceleration of the rotating frame, and so I apologize, but I'm going to have to go back up here again and grab that, and that was, I believe, omega 1 times omega 2 in the capital K. That indeed is right. Thank goodness for a little bit of a memory here this evening. Omega 1 times omega 2 in the capital K. I'm going to cross that with r of A with respect to B, which is r in the little j. I'm going to add to that 2 times omega, which we said was omega 2. Let me just double check here that I have my omega right. Omega 2 in the capital J minus omega 1 in the little I. And I'm going to cross that with V of A with respect to B rel, which we said was minus r times omega 3 in the little I. I'm going to add to that, in this case, that's my Coriolis term, so I need to add now my triple product, which is going to be the omega. So omega 2 in the capital J minus omega 1 in the little I, cross with quantity omega 2 in the capital J minus omega 1 in the little I, cross with r, which is r and a little j. Let me add some more space here to my notes so I can expand everything out. So if I do this, bringing the first term down, I have AA is equal to minus omega 2 quantity squared times b in the capital I, minus omega 3 quantity squared times r in the little j. I can come back up here above and note that little j can be expressed as big J, and if I use that equivalency, k cross j is going to give me minus I, so I'll have minus omega 1 times omega 2 times r in the big I. If I look at the next term, I can replace the little i's by big I's. And if I go ahead and expand that out, j cross I is going to give me a minus k, so I'm going to have plus 2 times omega 2 times omega 3 times r in the big K. I cross I is going to go away. I'm going to add to that quantity omega 2 times capital J minus little I and big I are equivalent, so I'll have minus omega 1 in the big I, cross with quantity j cross j, replacing the little j with the big J is going to be 0. I cross j, replacing both with capital, is going to give me minus omega 1 times r in the capital K. If I expand this out, I'll have minus omega 2 squared times b in the capital I, minus omega 3 squared times r in the capital J, minus omega 1 times omega 2 times r in the capital I, plus omega 2 times omega 3 times 2 times r in the capital K. J cross k is going to give me a capital I, so I'm going to have minus omega 1 times omega 2 times little r in the capital I. And I cross k is going to give me minus j, so I'm going to have minus omega 1 squared times little r in the capital J. You'll note here that two of these terms add together, namely the 2 and the I, so if I group things here, I'm going to have minus omega 2 squared times b, minus 2 times omega 1 times omega 2 in the r, and that's going to be all in the big I direction. I'm going to add to that minus omega 3 squared times r minus omega 1 squared times r, and those will be in the big J. And I'm going to add to that 2 omega 2 times omega 3 times r in the capital K. And that, folks, will give me the acceleration of that point A. From here you can plug in numerical values for everything if you're given them, and you can work out the answer. Wish you all the best of luck. Take care.